Hello guys, and welcome to lesson 1Z of chapter 1, which is a preparatory course for GCE advanced level. I am Dr. Miles, your host, and you are at Maths 24 Super Channel or the GCE Maths panel. Please follow this lesson to the end and take the tutorial that follows. Laws of exponents and simplification. Any number written in the form a to the power n is said to be in index notation, where a is called the base and n the power or the index or the exponent. Let's recall the laws of indices as follows. A to the power m times a to the power n is equal to a to the power m plus n, and this law is called the law of multiplication. And according to this law, if the bases are the same and we are multiplying, we can add the powers. The second law is similar to this one. A to the power m divided by a to the power n equals a to the power m minus n, and this is the law of division, which holds if the bases are the same. For this second law, if m is equal to n, then this gives us a to the power m minus n to be equal to a to the power 0, and a to the power 0 equals 1. For the law of further powers, if we have a to the power m further raised to another power n, this gives us a to the power m times n, and this law is called the law of further powers. For negative exponents, a to the power minus m is the same as 1 over a to the power plus m. Similarly, a to the power m is the same as 1 over a to the power minus n. And this is the law of negative exponents. Now let's look at the law of roots, which has two parts. The first part is a to the power 1 over n is the same as, this one is actually the nth root of a, the nth root of a. This is part 1 of the law, which is on roots of rational powers. In this first case, the numerator is 1. In the second case, the numerator is different. It's not equal to 1. So if you have a to the power m on n, this is the same as the nth root of a to the power m, or the nth root of a, all of that raised to the power m. This is the second part of this law. So the first part is when the numerator is 1, and the second part is when the numerator is not equal to 1. However, some teachers can just combine this law into this second part and give it as a single law. Equally, don't forget that any number raised to the power 1 is the same number. Here are some exercises for us to go through, and let us take the following remarks. The number e is a natural number. We will mostly meet this number in the next chapter of logarithms, where the number e is a natural number with a numerical value of 2.718. That is to 3 decimal places or to 4 significant figures. So for exercises, you have to simplify all of these expressions. At the end of this lesson, we have multiple exercises and answers. Let's look at some equations involving exponents or indices. The equality sign means two things are equal. Thus, in solving equations involving powers or index or exponents, this is what we consider. If the bases are equal on both sides, we equate the powers, because if the bases are the same, the powers must be the same, and vice versa. So this is the trick. If the bases are the same on both sides, equate the powers, and vice versa. Let's take some examples. Example 1, 2 to the power x equals 2 to the power 3. In this case, the bases are the same, and therefore the powers must also be the same. Example 2, here the bases are the same, And we know that 5 is the same as 5 to the power 1. So this gives us the value of x to be equal to 1. Example number 3. We equally know that 1 can be written as 3 to the power 0. That is to make the bases the same. And this will give us the value of x to be equal to 0. Example 4. 2 to the power x equals a half. From the law of negative exponents, a half is the same as 2 to the power minus 1. And here x will be equal to minus 1. Example 5, 10 to the power x equals 0.01. We know that 0.01 is 1 over 100, which is 1 over 10 to the power 2, which equally gives us 10 to the power negative 2. Therefore, the value of x here is negative 2. Example 6, 2 to the power x equals 16. We equally know that we can express 16 as a power of 2. So this gives us 2 to the power 4 and x is equal to 4. Example 7, 5 to the power x equals 25. 25 is the same as 5 to the power 2 and therefore x equals 2. Example 8, 27 is the same as 3 to the power 3. Therefore x equals 3. Example 9, 1 over 4 is the same as 1 over 2 to the power 2, which is the same as 2 to the power minus 2. Therefore, our x is equal to minus 2. Example 10, if you look, you see that the powers are the same. So what we need to do here is to equate the bases, and that gives us a value of x equals 4. Example 11, we can express this x to the power minus 1 as 1 over x from the law of exponents. And when we solve, the value of x will be 1 on 3. Equally, we can write 3 in the form 3 to the power minus 1 and further raise it to the power minus 1, such that the powers cancel and we are left with the same 3. In this case now, the powers are the same. Therefore, x is equal to 3 to the power minus 1, which can equally be written as 1 on 3. Example 12. This particular case, we should take notes because this is a quadratic equation and the roots should be 2, which can be distinct or identical. So x to the power x plus 1 to the power 2 is the same as 3 to the power 2, and x plus 1 will give us plus 3, or x plus 1 equals minus 3. Why is this? Because the square root of 3 to the power 2 is either plus 3 or minus 3. And when we solve this, we will have the values of x to be plus 2 or minus 4. You can equally test this in the given equation. The notes are equally available on our blog. You can move to GCE Maths Panel online classes or classes online, and you can get it on Google Sites. Example 13. On the right hand side, you can express 8 as 2 to the power 3, and equating the powers gives us this simple linear equation, which when solved gives us the value of x to be equal to 2. Example 14. We can equally express the right hand side as 3 to the power minus 1, and equating the bases, we have 2x minus 1 equals 3, and x will be equal to 2. The previous 3 lessons have been on equations, absolute value equations, absolute value inequations or inequalities, and surds, and this lesson is on indices. The next lessons will be on logarithm, and then we will move to chapter 2, which is the theory of quadratics. So now let's look at these examples that we have here. To solve this equation, 2 to the power x equals 1 on 8. We just express 1 on 8 as 2 to the power minus 3 and x equals minus 3. The same with all of these other cases. So please, one most important thing is to resolve all of these examples. And the challenge that follows in this lesson, when you solve that challenge, please don't forget to upload your answer in our blog, where we can discuss what you have. Or if you cannot access it, you can leave an email or a comment on gcemathpanel.blogspot.com. For graphs of exponential equations or index equations, for example, y equals 2 to the power x, let us take an example of this. We will make a table of values for this function and then we will draw its graph. So let us start from -3 and end around +3, not to take the values to be far apart. So we obtain a table of this nature, and when x equals -3, 2 to the power -3 is 1/8 or 0.125. And the same with all of these values up to 2 to the power 3 is 8. Now let us sketch the graph. So we have -3 and 1/8 or 0.125. Let me just take the whole numbers to make it faster. -2 and a quarter. -1 and -1/2. 0 and 1. 1 and 2, when x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. We now link all of these points to a smooth curve, and this is what we obtain. So this is the graph for y equals 2 to the power x. Normally, they can give you this graph and they ask you to sketch the graph of y equals 2 to the power -x. In that particular case, you will just have to reflect this, perhaps. So at the end of this lesson, we will see what is to be done. We will take a very good example and we see how we can obtain the graph of a to the power -x from a to the power x. So at this point, I'm leaving you suspended. So one thing to note about this curve is that it exists only on the positive side of the y-axis. In this particular case, we are looking now at the graph of y equals log x base 2. Log x base 2. You can see that it resembles the other curve, but something here is a bit different. So this graph is existing only on the right hand side of the positive side of the along the x-axis, because the logarithm of negative numbers is not defined. If x is negative, this logarithm would not be defined. That's why the graph exists only on the positive side here. So on this graph equally, the line y equals -x, or y equals, let me call it the negative y-axis, is an asymptote. The curve approaches this line but never touches it. Equally, an intercept here, this is an intercept. An intercept is the point where a curve crosses an axis, whether the x or y axis. Here we have the x-intercept because it has crossed the x-axis, and it crosses when x is 0, giving us the value of y to be equal to 1. Don't forget that the log of negative numbers is not defined. The log of negative numbers is not defined. So on this graph, when x is 1, y is 0. When x is 1, y is 0. I made a little omission before. Now we're discussing about how we can obtain the graph of y equals 3 to the power x from y equals log x base 3, and vice versa. So for logarithmic and exponential functions, when you convert to the other form, to obtain the graph of the other one, we just reflect along the line y equals x. So this is the graph of y equals 3 to the power x, and this is the one of y equals log x base 3. So logarithms and exponential functions are inverses of each other. As you can see, when you reflect one on the line y equals x, you obtain the other. So this is illustrated in the following graph of y equals log x base 3 and y equals 3 to the power x. However, this has not still answered that question on how to obtain the graph of a to the power minus x from a to the power plus x. We are still moving to it. Here equally we have multiple examples as well with solutions, and we have this challenge. Please, when you solve this question, you leave your comments under this video or you upload in the blog. We would like you to express this number in the form a to the power n as an exponent, a single base and a single power. So this gives us the answer of the last question, how to obtain the curve of y equals 3 to the power minus x from y equals 3 to the power plus x. So how do we do this? We just reflect this on the line y equals, let's call it the y-axis, or the line x equals 0. So this is what happens. This is how we obtain the curve. Thank you so much, guys, and stay tuned. You have been at the Disney Math Panel, and our next lesson is logarithms. Please don't forget to subscribe to this channel and encourage us. There is equally a quiz attached. Don't forget to take it or join our online math preparation classes for various exams. Thank you.